We discussed in this video about the probabilistic formulation of the principal component analysis. And the way we go about this is similar as we had before, but we are adding this idea that our variables are really random variables given by Gaussian distributions. So what we have this time is really we are going to have in the principal component subspace, we have a variable z, and this has m dimensions. And we are going to assume in this probabilistic model that z is a random variable and it's normally distributed with mean 0 and covariance given by the identity matrix. And what we had before in terms of the dependence between your original data space and the principal component subspace is now going to become x equals b times z. B is given by the matrix where you place the eigenvectors, the orthonormal basis of your principal component subspace on the column. So it's b times z plus mu. That's the mean of your data set, and then you also have some noise, and this is going to be a data point as we had before over r to power d. So what we have in here is the epsilon is normally distributed. So this is the noise because you want to have this as a random variable that is really given around mean mu, so epsilon is of mean 0, and the covariance matrix is sigma squared times I. And B is just like before, is the matrix D times M, which corresponds to the principal component basis. And so if you think about it like that, you are going to have that. So this implies right away, simply because z is normally distributed and epsilon is normally distributed, it's going to imply right away that x, when you see it as a random variable depending on z and b and mu and sigma squared, this is going to be a normally distributed variable with mean bz plus mu and covariance sigma squared times I. And so if you want also to think about this joint probability distribution x and z given by b and mu and sigma squared, then this is obviously going to be the just like we had in some of the previous lecture, it's going to be the probability of x depending on z, b, mu, sigma squared times the probability of z. And now when we want to obtain the likelihood of this probabilistic model, so the likelihood of this model, what we get is this is in the form of what's the probability of x given by b mu sigma squared, and this is obtained again like we have had before, is really given by integrating z out of this distribution. So it's going to be the integral of exactly this expression by z. So it's going to be probability of x given z b mu sigma squared times probability of z, and z is being integrated out. And so when I'm writing this down, this one is this normal distribution, so it's going to be normal distribution of x with mean bz plus mu and covariance sigma squared times I times p of z, and z was this one right here, so it's a normal distribution of z with mean 0 and covariance I, and this is integrated by z. And this is something we have discussed several times before, also in the previous chapter. This turns out to be a normal distribution with mean mu and covariance exactly B transposed plus sigma squared I. And these are calculations that we have done in some of the previous lectures, and I'm skipping them from here. So the likelihood of this probabilistic PCA really comes down to having this normal distribution around mu, and with covariance BB transpose plus sigma squared times I. And this must look quite close to what we had in the deterministic version of PCA in terms of the reconstruction being obtained as a product B times B transpose times the original data point. Now, if we also want to calculate the posterior distribution, so again, in the same way that we have discussed in the case of regression, so you have some idea about the distribution of Z, and then you see some training data, and you want to update your knowledge about Z. And so this, in this case, is coming as the probability of Z given some training set X. And again, by doing all these calculations, it turns out that this is a normal distribution with mean M and covariance C. And what M is, after you do these calculations, M is going to be exactly B transposed times B transposed plus sigma squared I, and this is 2 power minus 1 times X minus mu. This resembles some of the calculations we have done in the case of linear regression, and so for that reason, these calculations are skipped also in your textbook and also in these explanations I'm giving. And the covariance is simply I minus B transposed B transposed plus sigma squared I 2 power minus 1 times B. And again, these are calculations that we have done in some of the previous lectures. So there you have it. This is in a nutshell, without insisting more on this topic, but this is in a nutshell the probabilistic formulation of PCA. And what this comes down to is simply this idea that you will have your principal component subspace projection as a random variable and with a normal distribution, and your original data is going to be a normal distribution given by this one. And then using these model formulations, then you can start thinking about the likelihood of your model and about your posterior distributions in a very similar fashion as we have done for linear regression.